everybody. My name is Robert Fish, and I am a member of the Value in Nature Programme Coordination Team, and I'm the chair of tonight's proceedings. And tonight is a special occasion. It's the fifth in a series of lectures which are essentially exploring concepts, ideas, controversies, shall we say, around the matter of value in nature from different vantage points. So it's the fifth one, and these lectures have served different kind of purposes and different sorts of questions they've addressed. Some have been about connecting value in nature concepts to new areas of scholarship. So we've had lectures on rewilding and value in nature. Some of our events have been about really exploring stubbornly persistent themes in that kind of value in nature space, such as the moralities and ethics of value in nature in terms of money and the implications of that kind of idea. And also, to some extent, testing our own conditions of existence. So one of our value in nature lectures was actually moving beyond, heaven forbid, natural capital and ecosystem services. And I should just warn our speaker tonight that every lecture is a hard act to follow. So, you're the fifth in line. But the essential thing is, these lectures are designed to renew our discourse, renew our ideas, and to recognise that many of the ideas which we explore in sort of the value in nature space are never sort of finally resolved, never beyond revision, and the lecture series sits within a larger set of activities as part of the Value in Nature network, and that's a large and indeed diffusely emerging area of sort of scholarship and practice that tries to explore this agenda in all its kind of diversity, and it does seem to me, as one of the programme coordinators, that we seem to have a value in nature event every day. I'm not even quite sure which event I'm at. Last week we had, for instance, just to give a sense of the diversity, we had an event at the National Gallery that I was holding, which was exploring the role of the arts and the artists in value in nature research and how art interacts with the sciences. In a sense, continually sort of testing and exploring the boundaries of this kind of interdisciplinary arena. And alongside all those value in nature network activities, we have a number of significant research projects. So this programme, for those of you who are aware, is supported and led by the Natural Environmental Research Council, with other research council, and it's committed sort of significant investments of research council money into empirical research projects around different kinds of themes. So, for instance, exploring the links between natural capital and ecosystems, services and health, exploring ideas of tipping points and resilience. So we funded a number of projects in this area, but what surrounds that and what is crucial to our work is this sense of constantly kind of renewing our discussion, and that's what this is all about. And one of the other things that these lectures do, apart from connecting to new areas or revisiting old themes, is that they try to often get to fundamental sort of questions around which this whole agenda turns. And it seems to me that tonight's lecture is, in a sense, addressing one of those kind of core sort of issues. And despite the sort of the genericness of the title, in a way, in the nicest sense, what lies beneath this, it seems to me, who someone's watched this agenda and participated in it and contributed to it somewhat, this link between biodiversity and ecosystem services is a crucial one. It's a crucial one because when we think about the sort of provenance of this agenda in ecology, often that question about the link to biodiversity is often seen, is actually this kind of debate actually, does it sort of challenge some of our ideas around biodiversity, and how does biodiversity fit in? And it's not exactly a mystery, or it certainly won't be. It won't be at the end of this lecture, but it is a kind of crucial, it is a crucial one. It is a crucial one. And we're very lucky, given that, that tonight's Tonight's lecture is going to be given by Paula Harrison, who is Professor of Land and Water Modelling and the Principal Natural Capital Scientist at the Centre of Ecology and Hydrology. And what you should know about Paula is that she is very much involved in all of these debates, both empirically, scientifically, but in terms of influencing these kind of agendas, in a range of sort of policy arenas, including the Intergovernmental Science Policy Platform, Biodiversity and Ecosystem Services, IPBES. She's coordinating author for the Intergovernmental Panel on Climate Change, and of course she's been on home territory in a lot of her work also in terms of the sort of national ecosystem assessment, of which many people in the value in nature space participated in to different degrees. So we're delighted to welcome you here today, Paula, for giving up your time. It's a continuation of activities, meetings in DEFRA, meetings in Cardiff tomorrow, and you've managed to fit in a 45-minute lecture. So we're delighted for you to be speaking. Paula's going to speak for 45 minutes. I'm also joined here by two of my colleagues who are also on the programme coordination team for Value in Nature, Professor Michael Winter and Professor Rosie Howes from Centre of Ecology and Hydrology. And once Paula has spoken and explained some of these mysteries, maybe, I don't know, sorry, building you up. Once we've had this, once we've had your intervention, your lecture, it will be an opportunity for our panellists, Rosie and Michael, to respond, and me in the capacity as chair to open it up to what I hope will be a very stimulating discussion. So I thank you for all coming to this event, and it's lovely to see you here, and I'm just to say over to you, Paula.
I think you stole my notes as well there.
Oh, I did. Yeah, well, I'm sorry.
After bigging me up and then stealing my notes.
Sorry, I can give it for you if you want.
Yeah, go ahead. Okay, so thank you, Rob. It's great to see everybody here. So thank you very much also to the Valuing Nature programme and the coordination team for inviting me to give this lecture. More worried about it now after the build-up of what I've got to follow, but let's see where we get to. So, as Rob was saying, I'm going to focus my talk on linkages, and that's linkages between biodiversity and ecosystem services, and how they also link with drivers of environmental change. So what I want to start with is just to start with a bit of background on all the different components that are involved in the title and topic of my talk. And at the same time, I want to just sort of lay some of the groundwork about how those linkages could be portrayed conceptually. And I'm sure we'll recognise many of the diagrams that I'll show in this very first part of my talk. After that, I want to then move on to what is some of the scientific evidence that is out there that actually underpins some of these linkages. And how can we better structure that evidence to actually make it more readily accessible to both decision makers and other researchers, because we're crossing many disciplinary divides. I'll then finish with how we can use that knowledges on those linkages and some of these interdependencies that exist between our human and our environmental systems to actually try and simulate what does this mean for taking a whole systems perspective to look towards sustainable solutions when we know our future is uncertain and we don't know how that will unfold. And I'll talk about some modelling applications then that try to bring this information together on the different linkages between biodiversity, ecosystem services and drivers of environmental change. So, I'm afraid this might be very, very familiar to many of you in the room, and I do apologise for that, but I think just to get everybody to the same level and to avoid confusion later, I am just going to start with some common definitions. So, of course, I talk about biodiversity in my title. This is a definition that is a shortened version from the Convention on Biological Diversity, but basically this is the variety of life, including all plants and animals and the natural systems that support them. What's not included in my title, but that I will refer to quite extensively throughout my talk, is natural capital, which is the stocks of the natural assets that provide value for people. And those stocks of natural assets can be living components, such as species and ecosystems, and hence overlaps in part with the definition of biodiversity, but they can also be non-living components, such as fresh water or minerals. And I'm mainly going to be focusing a lot of my conversation today on the biotic attributes of natural capital. So those elements of biodiversity that produce value for people and underpin flows of ecosystem services. Which leads me to the next definition that I'm sure most of you will be familiar with, which is the ecosystem services, which are those flows of benefits to people in society that contribute to our human well-being. These, as many as you will know, can be provisioning services such as food we eat, timber or water, a whole range of different regulating services, so how we can regulate our climate through different vegetation, how we can regulate the flows of water and mitigate flooding, or how we could mitigate soil erosion, amongst many other examples. And of course, how we can provide cultural services, such as recreation, or simply our aesthetic or spiritual enjoyment of natural areas. So as I mentioned, our natural capital assets, the stocks and condition of those assets, underpin the delivery of different ecosystem services. And this has been represented conceptually in many different frameworks. And this is just one that's from the Natural Capital Committee that some of you may be familiar with. Here we can see this is our stocks of natural capital, both living and non-living components, which can be attributed or exist within different land use categories and different land use configurations. These stocks of assets contribute to one or more ecosystem service. They're often combined with other capital inputs, so this could be human capital in the way of our knowledge, it could be produced capital in such as machinery, to produce different goods that are either consumed or used by people, such as food. Those goods provide benefits to people, and those benefits, if we wish, can be valued either in monetary or non-monetary terms. What's also highlighted in this conceptual framework is how we manage our land use and how we manage our natural capital assets that exist within those land uses will affect both the stock and the condition of those assets. And we also know that those land use sectors also don't exist in isolation. Land uses all interact with one another. So different land uses compete for land. They also compete for water. And if we introduce management interventions or policy options in one land use sector or one policy sector, then it is likely to have cross-sectoral effects or impacts in another sector. And sometimes those impacts can be unintended, so there can be unintended consequences if we're not aware of all those linkages and interdependencies between the system. So that's one element of some of the linkages and how they can be represented conceptually. The other area is looking at the whole issue of drivers of change. And drivers of change can be any natural or human-induced factor that either directly or indirectly causes a change in our environment, in the structure or the function of our ecosystems. And these can affect all the different components of our natural capital assets, how they interact to deliver ecosystem services, and how they provide benefits to society. There's a whole range of different drivers of change, and again, the drivers of change do not exist in isolation. They also interact with each other. Some common examples are shown here in the eco wheel from the US Environmental Protection Agency, such as climate change, land use change, and pollution, all direct drivers of change in the environment. But we also need to look at policy change and other changes, such as changes in demographics, such as population change, changes in our economy or our trade environment, changes in technology or innovation, or changes in society itself, how people behave and how people interact with each other and with their environment. All of this can place pressures on our environment and how its ability to deliver certain ecosystem services. Now, those drivers of change have been studied in a number of national and international assessments, and this is one of the tables from the UK National Ecosystem Assessment, which reviewed the impacts of drivers of change on both ecosystems and ecosystem services over the past 60 years. And one of the conclusions that I'm trying to draw out here is that the primary drivers of change over the last 60 years were identified as changes in the area and condition of our habitats. That includes land use change, changes in air and water pollution, and our overexploitation of particularly terrestrial and marine resources. The UK National Ecosystem Assessment also highlighted the importance of climate change and invasive species, which have had a lesser impact over the last 60 years, but are expected to have a very significant role in determining future change and future impacts on both biodiversity and ecosystem services. Now, some of those importance of those different drivers, I think, is also reflected in many other conceptual frameworks, but this is one I particularly like because it builds in the dependencies between the pressures of the ecological system and the social foundations that are really represented in the Sustainable Development Goals that came out in 2015. So this is Kate Raworth's donut of social and planetary boundaries. In this outer boundary in the donut, it represents the pressures on the Earth system. Those that are quantified in red, or those that are shown in red, have been quantified as exceeding our safe ecological limits at the global scale. So this includes climate change, biodiversity loss, land conversion, and nitrous and phosphorus loadings. Those in grey have not yet been quantified at the global scale, but we know they're also extremely important and likely to have large impacts on both our ecological system and our social system. And the social system in the centre shows some of the basic needs, the basic rights for human survival and for human well-being, such as food, water, health, education and housing. The shortfalls shown in the centre of the circle are based on the minimum agreed standards from the UN Sustainable Development Goals, which were agreed by most governments worldwide. Now, if we try to represent some of those linkages between the drivers of change on our biodiversity or our natural capital and how they influence ecosystem services and benefits, again, there's a whole set of conceptual frameworks out there. This is quite a simple depiction of those linkages that comes from the UK National Ecosystem Assessment that really just makes the point that those drivers of change influence our ecosystems and the services, but at the same time they feed back, because however we respond to those impacts will also affect the drivers of change. Now, what I want to do in the next part of my talk is to try and break down some of these boxes. Particularly, I want to focus on this nested set of green boxes, which basically summarises all of the linkages between biodiversity and ecosystem services in a set of nested 3 boxes, and we know the situation is more complex than that. So what I'm going to do is to introduce you to some results from a systematic review, while we try to look into that set of nested boxes in more detail. And here we reviewed 780 different studies that were published in the peer-reviewed literature that looked at the linkages between the different biotic attributes of natural capital and 13 different ecosystem services, covering a range of provisioning services, regulating services, and cultural services. Now, that review was structured around the idea of ecosystem service providers. And these can be an entire community or habitat, so it could be a lake or a forest. It could be a functional group, such as coniferous trees or pollinating insects, or it could be an individual species. Now, each of these ecosystem service providers has attributes such as the area of the habitat or the size of the species that affect how it delivers one or more ecosystem services. In addition, there are various abiotic factors or attributes that can also directly affect the delivery of the ecosystem services. They can also affect the ecosystem service providers themselves and hence indirectly affect the delivery of the service. So I'm just going to provide some results from this systematic review to lay some of that foundation. So this particular bar chart just provides a summary of the variety of biotic attributes that we found in the literature covering all 13 ecosystem services. So at this moment, I'm not breaking it down by individual ecosystem service. But what you can see is the colour of the bars represents whether the linkage was positive between the biotic attribute and the ecosystem services, which is the green, negative in magenta, whether it was mixed, i.e. both positive and negative in blue, or whether it was unclear in grey. What you'll immediately notice is there's far more green in the bars than there is in any other colours. So most of the linkages that are reported in the literature are positive linkages. Now this could be in reality what's happening. It can also be a bias in the scientific literature in that scientists tend to be publishing more papers on positive linkages than negative linkages. And in fact, you see the only attribute which comes up with mainly negative linkages is, not surprisingly, mortality rate. If we look more closely at some of the positive biotic linkages, we can see particularly that the area of the habitat or community was very frequently cited in studies as being important to one or more ecosystem services, but studies also cited that the structure of the habitat and the type of the habitat was also critical. Many studies also noted particular species that were important for the delivery of services, or functional groups, and also that the variety, the species richness, was also often important. But what's more important is to try and work out which attributes are important for which particular services. So what we tried to do then is break down that evidence and look on a service-by-service basis at what biotic attributes underpin the delivery of that service, or are cited in the literature as being important for underpinning the delivery of that service. So I'll just show a few examples, starting with water flow regulation or flood protection. And here we found that the majority of the scientific literature focused on the importance of habitat area in terms of the actual amount, size of the habitat, extent of the habitat, and the amount of vegetation in that habitat was generally of most importance for delivering the service of water flow regulation. And this was based on a lot of catchment studies that looked at stormwater flows both before and after deforestation or changes in vegetation within those catchments. Here we can see in these network diagrams the width of the particular lines here indicates the number of studies that were showing or citing this linkage as being important, and the colour indicates the direction, with green being positive or mostly positive and red being negative or mostly negative. And what you'll realise is that because we have mostly positive and mostly negative, is that all these studies do not agree even on the direction of change. Hence, a lot of these are that there's less of the dark green and the dark red and much more of the lighter green and the light red, which shows that the uncertainty or the context dependency that is out there in understanding some of these linkages. What was found particularly as well for water flow regulation in terms of the abiotic factors, there's, as you might expect, precipitation was flagged up in most studies, particularly precipitation intensity, which affects the delivery of the particular service. Looking at pollination, here most of the literature was citing the importance of functional groups and characteristics of functional groups, but it also mentioned quite specifically the presence of specific species and particularly the behavioural traits of those species in terms of their flower visiting behaviour, things like tongue length, and in their ability to deliver services to specific crops. What we also found was important that came out of many studies was species richness in a variety of different pollinators with different sizes and shapes and slightly different behavioural traits would deliver a better service. We also found that the presence of a semi-natural community or habitat close to crop fields also tended to provide the food and shelter required by pollinating insects and was necessary for the delivery of that service, particularly when crops are harvested. And then just to show another example, but this time from a cultural service, this one of the aesthetic landscapes. And here we found again that this service was almost entirely linked to the community or habitat set of ecosystem service providers in the literature, but here particularly it was the structure that was considered to be most important, particularly the physical structure, where more complex structures seem to be more aesthetically appealing. But also with certain features, particularly abiotic features such as steep slopes and water, were also found to be particularly aesthetic appealing and linked to the provision of this service. So I won't have time to go through the detail for all of the 13 services, but we did try to summarise some of that information into some of the key linkages that happen between different groups of ecosystem services and different types of biotic attributes. So first, if we look at first at the physical amount of vegetation within a particular habitat or ecosystem, this seemed to be particularly important for the air, water and soil regulating types of services. Here with these services, these ecosystem services, it was the amount of vegetation or the density of above ground and below ground vegetation that was particularly important for the delivery of the service. Second, the provision of supporting habitat. This was particularly important for ecosystem services that rely on animal species such as pollination, pest regulation or freshwater fishing. Then thirdly, a much larger group, which was the presence and the characteristics of particular species or particular functional groups. Now this could be broken down and interpreted for many different species, but in particular characteristics of, many different services, but in particular species were very important for the provisioning services in terms of crop, timber and fish species, but also in terms of other recreational type services such as hunting, bird watching, etc. Presence of functional groups was found to be particularly important for services such as pollination and pest regulation, but also for other regulating services where small leaved versus large leaved trees make a difference to the service of air quality regulation, or deep rooted shrubs versus shallow rooted shrubs make a difference for mass flow regulation. And you can start to build some of the picture up on which are the characteristics that provide better service delivery for the different individual services. And then finally, if we look at biological diversity, this was particularly important and flagged up for the services of food, timber and fish provision, but also for pollination and pest regulation. And physical diversity, as I already mentioned, was particularly important for the aesthetic appeal of landscapes, but also for other services, because it was many studies in the literature stated that more of a complex physical structure tended to provide a better service. So, for example, a service such as water flow regulation or water quality regulation. What we also looked at, besides the individual biotic attributes, was actually some of those linkages between the ecosystem services themselves that were cited in the literature, because many of these studies concerned more than one different service. This slide shows some of the positive interactions between the different ecosystem services. And here we can see some trends that we would clearly expect. So we can see food production is positively interacting with services like pollination, pest regulation, and the regulation of soil erosion, as one might expect. You also can see quite a large interaction between air quality regulation and aesthetic landscapes. That emerged from a lot of studies that were really looking at urban trees, which tend to provide both of these studies, these services simultaneously. We also found quite a lot of linkages between some of the regulating services such as mass flow regulation, water quality regulation and water flow regulation, and that was mainly emerging because of studies that were based in very multifunctional, typically forest environments, where all of these services are provided by one particular habitat. When we look at negative interactions, we found less of these in the literature that we looked at, but there certainly are some. You'll notice this one here between water supply and timber production. This is really quite context specific, and it was from studies that were looking at the effects of timber plantations that were in very water-stressed environments where it had a significant effect on water supply. Some of the main general trends you'll get from this particular network is that the provisioning services, which are the red nodes, tend to have more linkages, more negative interactions coming from them than some of the blue and the green nodes of the regulating and the cultural services. So, just from that snapshot of one systematic review that looked at quite a lot of studies in the literature, we know there is evidence out there, but that evidence is quite fragmented and it's quite difficult to pull together, mainly because a lot of the studies don't use terms like natural capital and ecosystem services that makes it easy to pull this information together. It takes a lot of searching, and a lot of individual researchers are doing this kind of work. But what would really happen is what would really help is a way of sharing and structuring that information to make it more readily accessible. And one approach we're looking into doing that is the development of evidence chains. And these evidence chains will depict the linkages between those stocks of natural capital assets, those flows of ecosystem services, and the benefits and values they provide to people. But in each step of the chain, we identify what the strength of the evidence is for each of those linkages, and we also provide linkages to data sets and where they're available to models so that people can know where to go to for further information. So this work is still ongoing, but I'm just going to illustrate what we're trying to do with a very simple illustrative example, looking at how trees as a natural capital asset affects the service of air quality regulation. So if we look at this very simple chain, here we know that trees are very effective at capturing air pollutants and removing them from the atmosphere and providing the service of air quality regulation. We also know this has benefits for human health because air pollution has negative effects on the cardiovascular system. And we know the beneficiaries that are most at risk are people with pre-existing conditions such as respiratory disorders or cardiac disorders. And those people often have acute effects from exposure to high levels of particulate matter. And those benefits to human health can be valued in terms of avoided medical costs, in terms of hospital admissions, or deaths brought forward due to air pollution. So what we can do with a chain such as this is look at what are the attributes related to trees that are important providing the service of air quality regulation. So the type and the number on the extent of the trees, and we also know leaf size is important. So we can start to break down some of the attributes that are important for each of those natural capital assets. We can do the same with the linkages. So we know many of these linkages can be modelled, or there is a response function that will describe those linkages. In this case, it's a response function describing the rate of pollutant removal by trees. We can also then look into the literature, and through expert knowledge, we can start to rate that strength of evidence. Is it quite weak? Is it quite strong? Is there differences in opinion in terms of the direction? And we can start to capture that information in scores and in narratives that explain the evidence behind the linkages, along with links to key studies that people can go to for further information. We can then start to pull all of that information together. So here for the chain, we would have for each of the nodes, we would have a set of attributes that would link out to the data sets that provide information on those attributes. For each of the linkages, we would have information to the strength of that linkage, the strength of evidence behind the linkage, and potentially also to a response function or a model that might give you more information on that particular linkage, in terms of it could be something very simple like a lookup table, or it could be a very sophisticated, in this case, air chemistry transport model. And we can start to build that information together and structure it in a way that makes it more accessible. So as I said, this is quite a simple illustrative example. What we want to start doing then is to start to look at the complexity in these chains, because we know there are drivers that affect each of those nodes and linkages, and we also know that so often to provide a service we need multiple natural capital assets and they interact with each other. So we're starting to now make more complex chains that highlight also drivers, highlight also abiotic factors and how they link with some of the other biotic factors, and to try and build a more complex picture as well as the simple picture. What we're working on then is developing an explorer tool that will allow people to actually explore these evidence chains. So this is partly dummy data, I must admit, here in this particular picture. So please, I realise you probably won't be able to read the words in any case and the symbols in it. But the idea is that these chains will be displayed in a similar way to the network diagrams I was showing earlier, in that we will have different line thicknesses to indicate the strength of that evidence and different symbols to indicate the direction of that evidence. And what a user can do is that they can choose to display different evidence chains, and they can click on different linkages and different nodes, and then a new window is opened up that provides a narrative on the evidence underpinning that particular linkage in terms of how we rate its strength of evidence and linkages to different data sets and different models and different key papers on the subject. The functionality of the Explorer tool is also currently being developed so that you can start to link different evidence chains together by common nodes. So that might be common drivers, or it might be common natural assets. So you can start to build a picture of which natural assets link to multiple ecosystem services. And we're also trying to build in the ability to be able to filter on strength of evidence. So if you're actually only interested in where the strong evidence is, you can highlight that quite quickly. Or if you want to more importantly know where the gaps in evidence are, where we need more research, you can do the same. So in the final part of my talk, I now just wanted to talk about how we might use some of that knowledge on some of those linkages between biodiversity, ecosystem services and drivers of change to try and simulate some of the impacts of environmental change on both biodiversity, ecosystem services, and how we can use that to look at what might be effective policy options and management strategies that takes account of some of those interdependencies. So here what I will talk a little bit about is the use of scenarios. I'm sure many of you are familiar with scenarios, but scenarios can be developed to combine consistent changes in multiple drivers. So we don't have to look at single drivers in isolation, and we can try and look at some of the consistent interactions between them. These scenarios can then be applied to models, and those models then allow us to look at the consequences of different scenarios or drivers of change, and to explore the effectiveness of different policy options and management strategies. However, a lot of models that exist out there are highly sectoral, and they exist usually in one land use sector. They don't often take into account the interactions and interdependencies between the land use sectors that I was showing earlier. So what is being developed now are sets of integrated models which take some of the sectoral models and build in some of the interactions or feedbacks that need to be represented between those different sectors. And that allows us to build an understanding of some of those interdependencies, and it allows the exploration of responses that may or may not have synergies or trade-offs across different ecosystem services and across different sectors, so that we can kind of minimise any unintended consequences or adverse impacts and try and capitalise on any opportunities. That is not a simple and easy task to create an integrated scenario modelling platform. It needs a lot of partnership working from people from many different research disciplines working together in an open and transparent way. And it's very important to also work closely with stakeholders in developing these platforms, because it's impossible to build an integrated modelling of everything. You have to focus on a specific purpose. You need to understand that purpose and build in some interactive and responsiveness into those kind of modelling platforms. So I'm just going to provide an example on one modelling platform that's been developed over a number of years, funded by 2 EU projects, these ClimSave and Impressions symbols in the slide. This is known as the ClimSave integrated assessment platform. It's been developed at 2 scales, one scale to work at Europe and one scale to work in Scotland. And its purpose was to look at responses to combined changes in climate and a whole range of different socio-economic variables. And to look at those at the cross-sectoral dependencies between 6 sectors, so between agriculture, forestry, water, coastal and fluvial flooding, biodiversity and urban development. And to do that, 10 different models have been linked together, and we have flows of data running between those models representing some of those interactions. So just to illustrate that with one set of interactions, because there are many, so we have a model that models changes in the extent and the type of urban development, and how urban development changes affects our hydrological regime, which in turn will affect the people that are at risk from flooding and where those people are located. Changes in our urban environment is very much influenced by population. It's where most people live, and that also affects demands from domestic and industrial sectors for water use, which affects how much environmental flows are left for biodiversity, and it also affects how much water is available for other sectors, such as agriculture in terms of irrigation. How much the land flooded also affects actually the types of agriculture that can be undertaken in different places, but also urban land expansion takes up land and can be in competition against other land uses such as agriculture and forestry, and hence what happens in terms of how land is allocated takes account of some of these competitions and some of these constraints on our rural land allocation. And of course, what happens in the way we manage our land and the land use that it becomes will affect our habitat availability and our habitat condition, which will affect biodiversity. So this particular modelling platform was developed as part of a participatory stakeholder engagement process, both at the European scale and at the Scottish scale. So we held here a series of 3 workshops in the 2 different scale levels. And what we did was we worked with stakeholders to ask them what are the key drivers of change for their region that they're most concerned about going forwards in the future, that they think will interact with climate change and that they need to take into account to make sure any policy options they design are robust into the future. So we work with stakeholders to develop a range of socio-economic scenarios based on those drivers of change. We also asked our stakeholders what are the response options and the adaptation options that you need this platform to be able to consider, to be able to address, so you can explore them in terms of what-if questions. So they helped also to define the adaptation options within the platform, iterating with us in terms of what our models can handle and what the stakeholders required. And they also helped provide some feedback on the design and the functionality of the platform. This just gives an illustration of the scenarios that were developed by the stakeholders in the 2 regions in terms of the drivers of change that each region chose to structure their scenario, although many other drivers of change are included within the narratives of each of the 4 scenarios that were developed in each region. So in Europe, the main drivers that structured the scenarios were economic development and innovation, and in Scotland it was more well-being and lifestyle and resource scarcity. This produced 4 different narratives of changes in drivers in each of those regions going forward into the future, and the stakeholders worked with sectoral experts to quantify those scenario narratives into the many socio-economic variables that are required as inputs to the integrated modelling platform. And this is shown here on the platform interface, where we have a screen that allows the user to look at different impacts of different combinations of scenarios. And here the user can select a time period, an emission scenario and a climate scenario, and at the same time they can choose either one of the socio-economic scenarios that they developed themselves, if they were one of the stakeholders that participated in our workshop. If they choose one of their own scenarios, you can look at how that scenario is quantified in terms of the socio-economic variables that it represents. And here there is a default value for each of the variables along with a range of uncertainty. But the user, you can also create your own user-defined scenarios by putting the slider positions wherever you want if you don't think population change would be 23% in a future defined by this particular scenario narrative. The system's set up to be very exploratory. It's not a decision support system, so it just allows the user to explore how impacts change for different combinations of different drivers as represented through scenarios. And then they can think about how might I respond to some of those impacts. So just to give a brief example of some of the results that would come out from such a modelling platform, this shows the changes in the area of intensive agriculture simulated for the 2050s under two different socioeconomic scenarios and a common climate change scenario going into the future. In this graph here, we see a lot of green shading, which is a very large-scale expansion of intensive agriculture across Europe. And this is reflecting the quite large increase in population, which is coupled with an assumption of no improvements in agricultural technology. We also have very poor economic performance, and this affects how much that this limits the food imports that come into Europe, so more food needs to be produced using the European land system. Alternatively, if you look at the riders on the storm scenario, you see a much more mixed picture. The blues and the purples are decreases in intensively farmed area, and the greens are increases. And this is reflecting slightly lower increase in population, but greater assumptions of increases in yields per unit of land area due to crop breeding or improvements in agronomy. We also have more trade going on, more imports that take the pressure off the European food system, and there are also assumptions on dietary changes which move away from meat in this scenario. And then we can look at what some of the cross-sectoral interactions might be for the water sector. Here the water exploitation index is a balance between water availability and water use by multiple sectors. And an index value of 0.4 or greater indicates river basins that are classified as severely water stressed. So what we can see in the should I stay or should I go scenario is we have a very large number of very severely stressed water basins, reflecting huge increases in irrigated production under this scenario, but also reflecting some of the assumptions in the scenario regarding water savings due to technological change or behavioural change, which are much more positive in the riders on the storm scenario. So it's an interaction of different interdependencies that produce those outputs. Now these changes in land use and water use will affect a wide range of ecosystem services, and this is illustrated in these bar charts, which I realise is very complex and I'm not going to explain it in great detail, but what it's showing firstly is that there's a lot of uncertainty depending on how you view some of the interdependencies and whether you look at drivers in isolation in terms of single drivers, or you look at multiple combined climates drivers of change. So just to explain, if we look at the bars that are related to food provisioning, the scale here is just relative changes for Europe as a whole, and the grey bars here are based on looking in climate change alone. So it's an extreme climate change scenario and a moderate climate change scenario, both of which are showing decreases in food provisioning at the European scale with some uncertainty. When we look at the green and the red bars, this is looking at combined changes in climate and socioeconomic scenarios. And here you can see we suddenly now have very large increases in food provisioning and much larger uncertainties as well due to some of the assumptions in the social and economic variables. And what you start to see is you get different patterns across different ecosystem services depending on whether a service is driven primarily by climate, in this case, which often the water provisioning services are, or whether they're driven much strongly by the socioeconomics, which many of the land use related ecosystem services are. So one other result is looking at not only looking at single drivers versus multiple drivers, we can look at if we run different impacts associated with single sector models versus integrated models. So what we've done here is we've run the 10 models that are in this platform independently with no interactions between the models, and we've run them as an integrated system with those interactions and feedbacks. And this summarises the differences between running single sector models to look at impacts versus running integrated models. So what you can see that everything that's shaded green shows a magnitude of change or magnitude of difference of 50% or more at the aggregate scale for each of these European regions. What you also can see by these the double arrows is that for quite a few of the indicators you actually simulate a different direction of change, never mind a very different magnitude of change. And some of the indicators that were particularly affected by being extremely different are the biodiversity, the land use, particularly agricultural land use, and in part the water variables. And these are the variables that are particularly affected by linkages and independencies with other sectors. So just if we use one of these systems to try and look, okay, how would we then respond in terms of policy options or management interventions? In this particular system, you go to a screen called the Adaptation screen because it's mainly focusing on climate change adaptation under multiple drivers. And at this point in time, your scenario settings become fixed, but you can change different sliders to represent different policy options or different management options. And here, the magnitude of the adaptation that you want to implement is represented by the difference between your marker in your scenario setting and where you change your slider to. We also recognise that in all socioeconomic futures, there's not an unlimited availability of different capitals. So some adaptation options or response options need human capital, they need lots of knowledge, they need social capital, they need people to work together, or they need financial capital because they're just very costly policy options. So the green area limits the amount of adaptation that can be implemented depending on the socioeconomic assumptions in the scenario. And that is just indicative, it's not fixed, so it gives the user more flexibility. And if we look at how you could just use the platform in a very simplistic way, just to give an illustration of how cross-sectoral interactions might lead to unintended consequences. Here, this is just an example for if our policy aim was to try and reduce water stress on wetland species. So here we've got the bittern. What we might try to do is try and decrease water use elsewhere by increasing the efficiency by which water is used. So if in the platform we just simply increase the efficiency by which water is used, principally for irrigation in the agricultural sector, by the maximum that is possible in each of our socioeconomic scenarios, we can then have a look at what that does to water stress in the different river basins. What we find is that because we've made irrigation more efficient, we have reduced the cost of irrigation per fixed area of land, and in effect we've made irrigation more profitable. So more farmers have taken up irrigation, we have a much bigger expansion in irrigated production, and hence we have a much larger number of river basins at a high water stress than less. So it's had the exact opposite effect of what we were intending. And that's a very simplistic example just of some of these unintended consequences. So here you would just need to make sure you had constraints on water consumption at the same time as implementing adaptation options related to increasing innovation and efficiency in terms of irrigation use. What you can also use the platform to do is to look in more detail at different potential trade-offs and synergies between different strategies and what those strategies might aim to accomplish. So if you have a strategy that is aiming to accomplish food self-sufficiency or water efficiency, or to try and maximise timber production, or to try and improve nature conservation, you can start to play around with the system in an exploratory manner to have a look at the trade-offs it reveals. what we've done is these different sets of strategies we've run through the platform, and then we've tried to summarise some of the synergies and trade-offs that are shown at different scale levels. And in reality, you can start to combine the different options in different ways just to build that understanding of the interdependencies. So now I do apologise for the horrendous nature of this slide, and it's very difficult to show lots of very detailed trade-offs in any other way. So really all you need to see on this slide is the greens and the reds. Don't worry about anything else. What it's trying to show is these are the strategies at the top. So this is food self-sufficiency. There's a range of climate scenarios, a range of socio-economic scenarios to deal with different uncertainties going forwards and the drivers of change. And going down here, we have different ecosystem services. We have food, we have water, we have timber, we have atmospheric regulation, landscape experience, land use diversity, and then a couple of biodiversity variables, one in biodiversity in forest habitats and one biodiversity in agricultural habitats. What we can see if our strategy is to achieve food self-sufficiency, we can indeed, under most scenario combinations, actually improve our agricultural productivity and our food provision. But in doing so, our water provisioning and our timber provisioning and other ecosystem services go down. And you can start to look at those patterns across the different strategies and the different patterns of reds and greens. So that, for example, if you are looking at strategies that are more focused on the environment and on nature, again, you can get good outputs for many of the different ecosystem services, but at the same time, you are having less agricultural production, and here it has a negative effect for biodiversity that's in agricultural landscapes. So again, there are very simplifying assumptions. You need to understand the assumptions behind the modelling and behind the scenarios to interpret this, but it starts just to build up a picture of those interdependencies. So I'm going to try and finish off with a couple of slides of some of the conclusions. And first, these are more broad conclusions that understanding some of the linkages between biodiversity, ecosystem services, and drivers of change, what it does actually mean for us to try and look for sustainable solutions going forwards. And I think not just from the work with that one modelling platform that I've shown, but from reviewing different integrated scenario modelling studies across the literature, it becomes clear that trade-offs are pretty much apparent under all scenarios. So even scenarios that are developed for a sustainability goal will have some trade-offs within it. And how we deal with those trade-offs is really a political and a societal value judgment in what we want to do. Some of those trade-offs might be that we agree as a society to reduce our consumption of resources, so we are reducing demand rather than having to increase supply. But there are decisions that need to be made to deal with some of those trade-offs. When we've looked across different socio-economic scenarios and combined them with different direct drivers of change, looking at effects of climate change or land use change or pollution, we see there are certain characteristics of scenarios that tend to be more successful in mitigating trade-offs. And these are the scenarios that tend to be more proactive in the way they formulate their decision-making, rather than reactive in dealing with trade-offs. Also, those scenarios that are more holistic in the way they manage the human environment system in terms of taking mainstreaming approaches to integrate environmental issues across sectors rather than dealing with sectors in isolation. As well as some of those cross-sectoral synergies, we noticed that scenarios that deal with cross-scale synergies and trade-offs also tend to be more successful when you take the larger picture and you're not just then displacing your own impacts to somewhere else in the world, which is quite easy to do with these modelling platforms. If you just change your assumptions on trade or imports and exports, you can quite find you've got lots more land and water to play around with. But that just means you're displacing your effects, and you need to take that into account when developing these kind of solutions and testing different policy options. When we look at different types of policy options, often a different mix of options tends to be most successful. This is usually based on a mix of both quantitative analysis through scenarios and modelling, but also qualitative analysis, because it's very difficult to represent all of these types of instruments within models. But if we look at a different variety of supporting policy instruments, it helps us move more to sustainable development. But some of the experiments we have done with modelling platforms and in stakeholder participatory workshops, where we've developed pathways to a vision of sustainable development, really show the importance of societal transformation and getting society on board through behavioural change to reduce consumption, to build their social capital and become active citizens in multi-level governance. So finally, I just want to finish with a few implications as well for research. I hope I've shown that there is evidence out there on those linkages. I still don't think it's conclusive, and there are still many gaps, and there's a lot of work that needs to be done to pull it together and make it usable, particularly in decision making. And there are certainly gaps still in that evidence, particularly on certain ecosystem service and biodiversity relationships, but more generally on the effects of ecosystem condition rather than just stock, on the ability to deliver different services, and also on thresholds beyond which the delivery of a service is compromised. I also tried to show that I know single sector assessments have great value, and I don't want to say that they don't, because they're really important still for understanding the detail of specific processes and specific sectors and their own responses. But they need to be treated with caution when we're looking at devising policy options and management responses across connected human environment systems, and looking at the impacts of multiple drivers, environmental change, divides, and we also need to do it very closely with a whole range of different actors from different stakeholder organisations. So, thank you very much.